Very good morning to everybody. Welcome you all for the fourth session of classical unit. In this session, we will study about generalized coordinates and D'Alembert's principle. So let's recap of what we studied in previous class. Virtual displacement. An imaginary, arbitrary, instantaneous change in the position vectors of the particles of a system is known as virtual displacement. The work done by virtual displacement is known as virtual work. The principle of virtual work states, in a system of particles which is in equilibrium, if and only if the total virtual work of the forces is 0. The learning objectives of this session is to understand generalized coordinates. Using generalized coordinates, we generalize virtual displacement, generalized velocity, generalized force, generalized acceleration, potential and kinetic energy, along with D'Alembert's principle. By the end of this session, you will come to know how generalized coordinates are generalized with their physical quantities and D'Alembert's principle. Let us consider a particle moving along the circumference of a circle. Generally, we need r, theta coordinates to specify its position. However, if r is constant, only theta is sufficient to describe the position of a coordinate. Similarly, for a particle moving on a surface of a sphere, we need theta and phi. In general, the set of independent coordinates which are sufficient in number to describe completely state of a configuration of a dynamical system, which are represented by Q1, Q2, Q3, so on up to Qn, is called as generalized coordinates. The Cartesian coordinates can be expressed in generalized coordinates as x as a function of Q1, Q2, Q3, so on up to Qn. Similarly, y as a function of Q1, Q2, Q3, so on up to Qn. And z as a function of Q1, Q2, Q3, so on as a up to Qn. In general, the position vector of the ith particle Ri can be represented as a function of Q1, Q2, Q3, so on up to Qn. Let us consider the motion of a simple pendulum. Generally, we use motion in a plane is described in Cartesian coordinates x and y. However, plane polar coordinates is very good choice to describe simple pendulum motion. So old set Cartesian coordinates are now converted to new set polar coordinates. The relationship between old set of coordinates to new set of coordinates which are compatible with the constraint motion. This transformation from set of old coordinates to new coordinates is known as generalized coordinates. In this simple pendulum motion, the relationship between old coordinates and new coordinates is given by theta is equal to tan inverse of y by x. If the length of a pendulum is inextensible, only theta is sufficient to describe pendulum motion. So theta is equal to q1 is a generalized coordinates for a simple pendulum. Similarly, for a particle moving on a circumference of a circle, theta is equal to q1 will be the generalized coordinates. Virtual displacement. In the previous session, we learned what do you mean by virtual displacement. The position vector in terms of generalized coordinate is given by Ri as a function of q1, q2 up to q3n. Differentiating partially, this reduces to delta Ri is equal to summation I is equal to n dou Ri by dou kj delta qj. This is an expression for generalized displacement. The generalized velocity. The time derivative of generalized displacement gives you generalized velocity. The expression obtained on differentiating generalized displacement, we obtain Vi is equal to summation of I is equal to 1 to n dou Ri by dou qj into qj dot plus dou Ri by dou t. Generalized acceleration. The time derivative of generalized velocity gives the generalized acceleration. The expression for generalized acceleration is given by this expression. Now we'll learn about generalized force. We know that work done is a force into displacement. Delta W is equal to summation of Fi dot delta Ri. Substituting virtual displacement expression, we obtain generalized force represented by Qj, which is equal to summation of j to 1 to n Fi dou Ri by dou Qj. This is a generalized force expression. Potential energy. If the potential of a system is dependent on the position, then potential energy expression is given by delta V by delta Qk is equal to minus capital Qk. However, if the potential depends on the velocity, then potential energy term is given by capital delta Q is equal to minus dou V by dou Qj plus d by dt of dou U by dou Qj dot. The second term in this expression is a velocity dependent potential. Kinetic energy. We know that kinetic energy is given by half mv square. Expressing these kinetic energy in different coordinate system, we obtain kinetic energy of m x dot square plus y dot square in terms of Cartesian coordinates, kinetic energy of m r dot square plus r square theta dot square in terms of polar coordinates, kinetic energy of m r dot square plus r square theta dot square plus r square sine square theta phi dot square in spherical coordinate system, kinetic energy of m r dot square plus r square theta dot plus z dot square in terms of cylindrical coordinates. So far, we have discussed how the virtual work deals with the statistics of a system of particles. In general, to describe motion of a system, D'Alembert's developed a principle known as D'Alembert's principle, which states that the resultant force acting on a body together with the reversed effective force are in equilibrium. The expression for D'Alembert's principle is summation I is equal to 1 to n Fi minus Pi dot into delta Ri is equal to 0. This is known as D'Alembert's principle. So, in this session, we have learned what do you mean by generalized coordinates and the generalized coordinates for virtual displacement, velocity, force, acceleration, potential and kinetic energy in terms of generalized coordinates. We also studied D'Alembert's principle. Now let's have a small MCQs. Question number 1. Generalized coordinates. Option A, B, C and D. The answer is option A, depend on each other. Question 2. If a generalized coordinate has the dimension of velocity, generalized velocity as a dimension of acceleration. Option is C. If a generalized coordinate is angle theta, generalized force as the dimension of torque. Option is C. If a force is derivable from a potential, then such forces are called as conservative force. Option A. The expression is known as D'Alembert's principle or law. So you can refer for the sources: Classical Mechanics by Goldstein, Classical Mechanics by Gupta, Kumar and Sharma, Classical Mechanics by Takwala and Puranik, Classical Mechanics by J.C. Upadhyay. Hope you enjoyed this session. Thank you.